So I want to talk about the relationship between area and displacement because this gives us sort of a type of word problem that we can solve using area. So let's suppose that I have that I've graphed uh, I've graphed velocity against time. So at any given time, I know what the velocity is. And I'm going to do this with a really simple example. I'm going to say, let's suppose that I have a constant velocity function. I'm traveling at a constant 50 miles an hour. You can sort of imagine this as being like, if we call that north and that's south, sort of imagine that this is Route 1. And, I start here at I start at this dot. This is let's say the Harrison Street traffic light on Route 1, and I start driving north toward New Brunswick. I remember New Brunswick. I was there as recently as March 11th, 2020. So anyway, of course, in the coronavirus world, the speed limit is actually 50. When people were driving to work more, it was really more. The actual speed on Route 1 was more like 20. But let's say that we're traveling along at a constant 50 miles an hour. So the thing to note is that for every hour that you travel, you go 50 miles. So let's suppose that I've gone 1 hour. Then, if I've gone 1 hour, then the total distance that I've traveled is actually the area of this rectangle because 1 hour has a width of 1 and a height of 50. So 1 hour has a width of 1 and the rectangle is going to have a height of 50. If I travel for 2 hours, then the total distance that I've traveled is the sum of these two rectangles, or I could just call it one big rectangle. The point is that it's the area under the velocity curve that's actually giving me the distance that I've traveled. So the distance, or I should say that I really should say the displacement, and you'll see why in a minute. The displacement from my initial position equals the area under the velocity curve. Okay, so in one sense, if we had either a velocity function or we just had a number of values of the velocity itself, we could use that to estimate the total displacement that we had gone from the starting point. We can generalize this a little bit more. Like let's suppose that I have this velocity function, this green curve that you see. Look at what's happening. Recall that velocity is understood this way, that we sort of have the positive direction. We start at some point called the origin, and if we're moving to the right, we say that our velocity is positive. If we're moving to the left, we say that our velocity is negative. So here what we have is a velocity that's positive up until 2, and then it's negative and then until 5, and then it's positive again. So what we could say actually is that the in this region here, the object is moving to the right in an amount equal to this area. Again, we're equating the area under the velocity curve with the total displacement. Now, note what happens here when I get to the negative part of the curve. I'm still getting more area, but here the object is moving to the right. I mean, sorry, to the left instead of to the right. So here we're moving rightward, here we're moving left, and then we go back up here and we're moving right again. So then oops, sorry, I've got that. So then I have that area. So I can't simply add up the two blue areas and the purple area in order to find the displacement because here I'm moving to the right, here I'm moving to the right, and here I'm moving to the left. So if I give these values, I'm just going to make up numbers here that have no real connection to what the actual area is, but let's say that that's 1.5. Let's say that this is an area of 3, and this is an area of, let's say, zero point 0.5 right there. What we would say is that the total displacement is equal to 1.5 minus 3 plus 0.5, which actually comes out to negative 1. So as you can see, even though I could add up all these areas, we spend so much time moving to the left that we actually come out to a negative position, to a negative displacement. Because we have to treat areas that are under the negative, we have to treat negative parts of the velocity curve as retreating, in other words, moving to the left, so we subtract them when we calculate the total displacement. So this is kind of an interpretation of the velocity curve that makes use of the notion of area under a curve. Hopefully with this simple example, what you can see is that the area under a constant velocity curve just gives you the total distance traveled, whereas if in greater generality, if I have an arbitrary velocity curve that may be positive and negative, I add up the areas under the positive part of the curve and I subtract the areas that are enclosed by the negative part of the curve to get the total displacement.